and Eulias.
Eulalia. Ask Bill where he got his name.
Okay.
Okay. Thank you, Robin. I just wanted to point out that I have a number of collaborators listed here. They're part of this large spectroscopic survey of asteroids, primitive asteroids, that we have going, so they're listed there. I'm not going to go through all of them. I am a member of the Center for Lunar and Asteroid Surface Science at the University of Central Florida. I'm also a co-I on OSIRIS-REx. So I actually thank my two previous speakers for setting up this talk very nicely. Okay, so we just submitted 2 papers to Icarus, one by Pinilla Alonso et al. With the infrared results that I'll be reporting on today, and one by Julio de Leon et al. With the visible results. So here's a quick outline of the talk. I'm going to give you an introduction of NEAs and low albedo inner belt families, which actually can shorten thanks to Bill's talk. And then I'll tell you a little bit about our larger long-term project with the results on these 2 families, the Polana and Eulalia families, and then the conclusions. But just in case, here are the conclusions again. I like to do this in my talks just in case I get cut off at the end. So the Polana Eulalia families are dynamically complex. The Eulalia family is essentially all within the Polana family, but they're spectrally homogeneous. So that is our main result from our study of these two. We categorically reject a prediction by Walsh et al. In 2013 that the Eulalia and Polana families could be distinguished by their near-infrared spectra. We find that the background objects that we studied as part of our survey are spectrally similar to the Polana family and or Polana and Eulalia families. That means that the families are actually larger than we currently recognize. The 2 NEA sample return targets, Bennu and JU3, are compatible with our spectra of the Polana family. That doesn't mean that they're from Polana, but they're compatible. There are a number of papers that say that Bennu is likely to come from either Polana or Eulalia, this is compatible with that. The problem is the Bennu spectrum has been marginally constrained. For example, you saw the different spectral shapes that Bennu showed in Adrian's talk. Okay, so as Bill told us, the NEAs are not primordial. They come from the main asteroid belt, and this is from his 2002 model. It hasn't changed dramatically. The Yarkovsky then will tend to, the retro Yarkovsky will tend to move them into the new 6, so I'm not going to dwell on this. And so our 2 sample return targets, Bennu and JU3, come from the inner belt. They're both retrograde, and so they probably came to the inner belt, to the NEA population through the new 6. And the inner belt has several low albedo families, so let's look at those. And so this is from our paper in 2013. So we outline here, these are all of the major inner belt asteroid families, and outlined in black are the low albedo ones. So these are the Aragone, Polana, Sulamitis, and Clarissa families. And next, and by the way, so this is semi-major axis with inclination and eccentricity. And so next, what we have here is from the WISE data, we plotted all of the low albedo objects in the inner belt, low inclination low albedo objects in the inner belt outside the families. And what's interesting here is that this is the quote-unquote background, but you can see that the Polana family over here and the Aragone families are still represented in this plot that is supposed to be objects that are not in the family. So that basically saying that the families are larger than we had currently defined them as. Then, since we started our investigation of the inner belt low albedo objects, the Polana family now we know has 2 components. There's the paper by Walsh et al. In 2013 that identified Eulalia, and then a confirming paper by Dykes and Greenberg. I'll talk a little bit more on this in a second. So our survey, we call it PRIMUS, and it's the Primitive Asteroid Spectroscopic Survey. We have a number of telescopes looking at asteroids, and what I'm reporting on today was 128 asteroids, most of them not observed before in the near infrared. These are all the sites that we've been using: Mauna Kea, Chile, the Canaries. And so in 2013, Walsh et al. Identified the Eulalia family and predicted that Eulalia and Polana would be spectroscopically different in the near infrared. In 2015, Dykes and Greenberg confirmed the dynamical identification of Eulalia, but they found no difference between Eulalia and Polana in the SDSS colors. So this is a partial plot of our targets, but this illustrates nicely where the Polanas are, which are, at this this is semi-major axis versus absolute magnitude, and the blue lines define what's inside of the Polana family. And you can see then that the Eulalia region, which is in red, are the limits of the Eulalia region in red. It's entirely within the Polana family, except for possibly 495 Eulalia itself. So all the Eulalias are within the Polana family. So we actually looked at them spectroscopically in the visible and the near infrared to as part of our original project, but also to address what Walsh et al. Had predicted. And so we found that all 125 primitive objects within our sample were spectrally identical. And we also found that the parents, 142 and 495, so Polana and Eulalia themselves, were relatively similar in their spectrum and almost identical. And then we also, as I said, we reject the proposition that these two families could be distinguished spectroscopically. We also looked for a possible variability within Polana itself, and we found none. And there was a previous spectrum of Eulalia that had been published, and that is one of the reasons why Walsh et al. Predicted that they could be different spectroscopically. And then when we reduced that spectrum, we found that it was identical to ours. So the published spectrum, the previously published spectrum in 2008 of Eulalia is incorrect. And the other thing that we found then, we compared this with the spectra of JU3 and of Bennu, and we found them to be within the range of spectra that we found in this family. That doesn't mean that they have to be from this family. And again, we found that the background was essentially identical to the family. So that confirms that plot that I showed you from a 2013 paper that indicates that even when you remove the family membership, there's still clumps where Erigone and Polana are. So the conclusions again, Polana and Eulalia are dynamically complex but spectrally homogeneous. We don't see any spectral difference between Eulalia and Polana. The background objects are similar to the families, and therefore they are the families are probably larger. And again, Bennu and JU3 could be from within our Polana spectrum. Thank you. Andy Rivkin.
Humberto Campins. We meet again. Given the homogeneity of the spectra in that whole region and in the two families, how it looks like you keep observing the same thing over and over and over again. I wonder if you can comment on the reported heterogeneity on the surface of Bennu and also of 1996 FG3, where the one single, or I guess two different objects seem to show heterogeneity on the surface of this one asteroid versus the fact that all of these seem to look the same.
At the risk of being too technical, it beats the hell out of me. I don't know what's going on with Bennu. It could be that we're observing, indeed, I'm a co-author on the Binsel paper. It could be that we're observing slightly different parts of the surface. And the FG3, as you probably know, we did a lot of work on that, and we still don't fully understand why FG3 looks different and with different, same observer, different, only slightly different geometry. So I'm puzzled. The solution to this is you observe an asteroid once, you declare victory, never observe it again.
Hey, Humberto.
There's a few other interesting dark families that were on your plot from a couple slides ago. And
that was according to Nesvorny at that time, but yes.
oh no, I mean even further back you had like the Aragoni members and everything else.
Yeah.
And what I was wondering is what are of the families that are still low albedo there? What do their spectra look like? Do the Aragonis also look like the Polanas and Eulalias?
No, they don't. As a matter of fact, we as part of our ongoing project, we already have the Aragoni family fairly well characterized. They look. They don't have any blue objects within the Aragoni family. They all look flat. The Polana family has a large fraction of objects that in the visible they are blue, and also in the SDSS colors, the ones that where you have high enough signal noise. And we started a survey of Sulamitis. So Aragoni have fairly well characterized. One thing about Aragoni has a large number of their members with a 0.7 micron feature in the visible that is indicative of hydrated minerals.
Because as you know, on the paper we're on together, a year or two ago we published something on where Bennu possibly comes from.
Right.
And we talked a little bit about the Hayabusa 2 target, but now we're talking about 2008 EV5, which has got a high albedo, and I'm not sure where to link it to. So so we need to find the source for that, and so that's the next question.
Let's talk about it offline, but I think that EV5 could potentially come from this relatively high albedo, low albedo, high inclination group, but I don't know. So it's within the limits of something that would produce something as low albedo, as low inclination as EV5. But we can brainstorm on that one.
Okay.
But yeah, so I agree with you. What happens here is here's basically the shadow of Aragoni in the background, and here's the shadow of Polana in the background. But you can see that a big chunk of the background is actually these two families. And then here is some of the Sulamitis and the Clarissa. Plus, then there's other group that has not been identified with the family. So I'm hoping that a dynamicist would tell me where those come from.